Hi, welcome to the 5th lesson block. Today we'll talk more about 3D space 3DEqualizer and start building a scene from reference photos. I'll delete the main camera. And load the reference photos we've already used, though this time we'll take a slightly different approach. I'll add 2 reference cameras. So we've loaded 2 reference photos, and from them we can start building a scene that will later help with tracking. You can switch between the reference photos using the left and right arrow keys, and we begin by projecting points for all the reference photos. I hold Ctrl and click to create a point, then press the right arrow to move to the next photo and project the same point in the same place. We do the same for the other points. 1 point across 2 photos. We can enable center on 2D point mode, and then when switching between photos we can check how accurately we hit the same point. You can place several points at once. For example, 1, 2, 3. I created 3 new points, switched to the next reference photo, and use the up and down arrow keys to navigate between the points in the point browser. I selected the second point, press down, and move to the next point. Press down, and move to the next point. The main thing is not to mix up the points. To check, I also switch left and right. You can place a point and press track. 3DEqualizer will try to find that location on the other photos. The key is that the difference in angles between the reference photos should be small. If the camera moved too much, the program might not find a match. If the steps are small, the search will succeed. You can choose to track across all photos, or just forward or backward to the next reference frame. And here it found the same spot in the next photo. Let's place a few more points. The main thing is not to mix anything up and make sure you're projecting the same single point in the same spot across all photos. Let's keep it like this. We need to set the correct camera parameters right away so everything solves correctly. Now let's try to solve the camera, or rather, in our case, solve the positions of the reference cameras relative to each other and compute the scene. Here we can see how the 2 reference cameras are positioned relative to each other and the points we projected from these reference photos. Overall, we can see that this is the chair, this is the countertop. Maybe not everything is perfectly aligned yet, but we'll work on that. Let's switch to 3D orientation. The image plane will get in the way here, so let's hide it. Menu, View, Show Image Planes, None. Here's an initial view of the points we projected in 3D from the 2 angles. It's not all perfectly accurate yet. For higher precision, we'd need more photos. For now, we can see that the points are fairly even if we straighten them a bit. In general, just relying on points makes it hard to determine the exact placement of objects, so we can build proxy geometry, basic 3D objects that can later be exported to a full 3D editor. In 3DEqualizer, there are sections for geo objects and 3D models for this purpose. Essentially, both geo-objects and 3D models are placed in 3D space. Geo-objects are reference lines and guides without their own properties. 3D models are geometry objects with defined properties. For example, to create a guide between points, select 2 points, then go to 3D orientation. Geo, create, line strip. And now in 3D space a line appears, which makes it easier to orient yourself. You can see it's a vertical guide corresponding to the selected point in the location. This is a way to visually mark objects more clearly. To do this, 3D orientation, Geo, create, line strip. You can also select points and press Alt-L. We already have an understanding of where things are and where the camera is relative to them. Geo-objects don't have properties. When you select an object, nothing appears in the properties panel. You can find these objects in the point group structure under the Geo-objects category. They're all listed there. We can also create geometry. For example, we can stretch a polygon between 4 points. Take 4 points that lie on the chair's surface at the corners of the seat. In 3D models, choose Create. Here you'll find a standard set of objects: cube, cone, cylinder, sphere, and others, as well as the option to create a custom mesh. Legacy and advanced skinning are methods for creating a mesh. Legacy is not outdated, as the name might suggest. It's a simpler method, suitable for basic geometry and small objects. Advanced skinning is designed for dense point clouds to generate geometry from them. However, the quality is lower than in specialized photogrammetry software that's specifically made for point clouds. So if you need to build geometry from a point cloud, it's better to use dedicated software like PhotoScan or Reality Capture. Legacy is convenient for quickly creating a mesh without complex processing. Legacy, create. Here is a polygon. And on all the reference photos, we can see that it sits exactly where the chair is. Let's switch back to 3D rotation controls. You can select the polygon, like any other object, either in the viewer or by finding it in the point group under 3D models. When we click on a 3D object, we can see its properties. Let's come back to the properties in just a couple of minutes. For now, let's straighten our scene a bit. We remember that we can set a point's position in its properties. For example, if I want to place this corner at the origin, I select the point, open its properties, choose exactly serve it, and enter the coordinates, in this case, zeros. Then I resolve the camera, so the scene updates with the new point data. By the way, we can see that in 3D space, this point has moved and the line no longer looks vertical. When resolving the camera, you don't need to delete polygons, geo-objects, or guidelines. They remain linked to the points they were created from. Calc all from scratch. And now it's recalculated with 0 at the base of this line. We can also check the coordinates that 3DEqualizer assigned to other points whose positions we don't actually know. To do this, select a point, either here or in the point browser. Here its coordinates are displayed: 29.6 on X, 49.7 on Y, and 10.42 on Z. By setting the scale, you can understand the coordinates of other points without specifying them directly. These data can be exported to a 3D editor. For example, the height of this table is roughly 50 centimeters, but you can specify it more precisely in the point properties. 87.5 centimeters. And likewise, it's at 0 on X and 0 on Z. The coordinates have changed. And since this line intersects with the vertical, I know that's 0. So here we can also set both points to 0 on Z. I don't know their height yet, but after resolving it will be determined. The height of this point plus the height of the countertop, which I don't know yet. So x-axis I don't know, I'll disable it. Y-axis, that's what I want to calculate. Z is 0. We switch to 3D orientation, and now our scene is already a bit more properly aligned. Things are a bit off, and that's because we only have 2 reference photos. I think we need to add one more. By the way, the countertop height at the moment is 92.2 at this point, 91 at this one, 89 at that one. There's some error, but we'll add another photo and straighten it out. Let's add one more reference camera. And place a photo in it. The third photo. As before, switch between photos using the left and right arrow keys. Add a few points on the new photo. For example, select a point, press right, find the same spot on the new photo, and place the point there. Let's start by placing 4 points that are at the farthest corners of the scene. and solve. Now we have the third reference camera solved using these 4 points. If we switch to lineup controls, we can see that not all points are perfectly aligned. For example, here and here the points aren't quite exact, but based on the first 4 points, the new camera is already more or less oriented. To make it easier to orient the roughly solved scene, we can switch to manual tracking mode and enable the display of 3D points here. It's a bit like lineup controls, but in manual tracking we can place points, whereas in lineup we can only select them and rotate the camera. So in manual tracking, I select a point and immediately click where it should be. I select the next unplaced point, click where it should go, and continue like this. This is more convenient than switching to the previous camera, selecting the point there, and switching back. Here we can see where the solved 3D point corresponding to this corner is, and simply refine its position. We apply it and go to 3D orientation. A new camera. It hasn't become much straighter, so let's attribute that to distortions and tweak it a little. And we'll adjust it across all 3 photos. Adaptive all instead of brute forcing. Since computing the full range of all 3 parameters sequentially takes quite a while, we'll use adaptive. This way, the program adjusts values in the direction where the error is smaller. So we don't compute the entire range of values, but move in the direction where the error is smaller. When solving many parameters, this method is better. If there are only a few parameters, brute force is preferable. The key is to understand the difference between these solving methods. We transfer the parameters and resolve the camera. We transfer the parameters and resolve the camera. And now it already looks, I'd say, quite straight. The countertop height is currently 91.2, 91.8 and 92.1 centimeters. The real countertop height is 91.5 centimeters. So overall it's very close. If we had more photos, the result would be even more accurate. Let's create one more point and go over the properties of 3D models. Manual tracking. Create a new point. It seems that when trying to track a point backward from this angle, the program might not find the corner on the previous frame, because the photos were taken from very different positions. Yes, between these 2 frames the program can easily find the point. We check and press track. I got lost and didn't find it. No worries. But from here, it will find it. Go to 3D orientation. You can create a cube at this point via 3D models. Create cube. It was created at the origin. It's worth noting that 3DEqualizer's 3D space isn't the most convenient as of 2020, so building full 3D scenes here is tricky, but you can create references, proxy objects, export them to 3D editors, refine them, and then import them back into Equalizer. You can export all created objects as an OBJ, 3D models, export 3D models, OBJ, and later, if needed, import them back via import OBJ. And geo objects can also be exported separately as an OBJ file. What we can do here with the geometry that 3DEqualizer provides, in general, let's quickly go over the properties of 3D models. Identifier, the name of the 3D object, shown in the model list. The checkbox model contains service data indicates whether this model contains additional data about its position in the scene. If the box is unchecked, there's no such data. This setting is enabled by default for OBJ files that we import, and by default it's disabled for objects created inside 3DEqualizer. Manually created objects are usually moved and modified without using them as a source of tracking data. Imported objects, however, can be used to obtain coordinates from the geometry. If you check model contains service data, the object is locked and cannot be moved. When I say an object contains service data, it means its coordinates are fixed. The corner always stays at those coordinates. The plane always lies in that plane. When I disable service data, the object can be moved and its coordinates can change. This might sound confusing, but we'll clarify it in the next example. The reference-only checkbox means that if you import a model from disk, 3DEqualizer doesn't copy it into the project, but keeps a link to the original file. If the geometry is large, this prevents the project file from growing, since the model stays on disk and isn't embedded in the project. Performance rendering is used when working with large or heavy objects, such as a point cloud from Photoscan. If the geometry is too large and 3DEqualizer starts to lag, you enable performance rendering. You can also adjust the rendering quality parameter to control display quality. In this mode, the model is shown in a simplified form, making it easier to work with large geometry. Proxy geometry works similarly to shots. You can load the main model, a low poly version, or several variants with certain elements enabled or disabled. If they share the same coordinates, you can switch between them and the geometry will be swapped in the viewer. This is convenient for working with different versions of models. Import is the path to the geometry file, for example an OBJ. If a 3D model object was created inside 3DEqualizer, it doesn't have a file path on disk. It's stored inside the project, so no file reference is needed. For an external model, the path will be shown here. The Show 3D Model buttons allow you to show or hide the model and also adjust its color and transparency. If the object has a texture, you can load it via View. Load texture and select the texture file. Then specify the projection method, none. Default texturing is disabled. UV mapping if you want to use a UV map. Project from camera to project the texture from the current camera onto the polygons in the 3D scene. You can display points using the Show Points option. They will appear in the 3D viewer, small but visible. Show lines, polygons, hidden lines. By default, the usual polygon orientation is used, but there's an inverting option that flips the normals for visualization or if needed. You can attach a model to a point instead of placing it at specific coordinates. If you set a model at fixed coordinates, it stays there with every camera solve. If you attach it to a point, the model follows that point whenever it's recalculated, moving smoothly with it. Some specifics of 3DEqualizer. For example, the pivot of a cube model by default is at the bottom center. You can see it. It's at the origin. To move the pivot, you need to use a script. You can select the model and use one of two scripts in the 3D Models menu. Move 3D Pivot to Origin, moves the pivot so it's at the coordinate origin. Move 3D Model, Pivot to Point, selects a point to become the model's pivot. Both methods let you control the pivot's position, but the interface is inconvenient, so scripts are needed. For example, if I want this corner to be the model's pivot, here's what I do. I move the cube. But since Equalizer still has small scale issues, it looks a bit odd. Ideally, I should move the cube by -10 on X and -10 on Z. Next, I run the script 3D Models. Move pivot to origin. But due to the small scale quirks in Equalizer, the result ends up looking roughly like this. Now the pivot is at this corner. If we want the pivot to be any point that works without issues, there are no scale problems in this case. We can move the model using Translate, Rotate and Scale. Translate enables the move mode, letting us drag the cube along the axis to shift it left or right. We can also enter precise values for position, rotation, and scale. These handles always retain the scale they were last set to. Their size doesn't depend on the scene or camera scale. You can adjust the handle size using the numpad plus and minus keys. Now we can attach the object to a point. Select Snap to Point, open the point browser, choose the point you want to attach the object to. For example, point 13. The object will move to that location. We can change its size to fit it to the object's dimensions. And make sure it sits more or less correctly from all angles. Of course, this can be refined by adding trackers, but I think it's enough for our example. And even a scene like this can now be exported to a 3D editor via 3D Models, Export Models, OBJ, or used here to refine the track and work with tracking. In this scene, some points have known coordinates, while others are recalculated each time the scene is solved. If we're confident that all points are correctly placed, it's not necessary to recalc them every time. We can effectively bake the tracking with known coordinates. Working with points that have known coordinates is always easier and more convenient than with unknown ones. For example, if points have no coordinates and are in survey-free status, you need 6 points between root frames. If the points have coordinates, only 4 points are sufficient between root frames. And this immediately gives depth information. It's much easier to track when we have data about geometry, measurements, and spatial positions. To avoid recalculating these points every time and bake them, we can select a point and go to Edit, Convert to Survey. If a point is already partially known, for example, we only set Z, it will become fully locked. If you select a point whose coordinates are unknown and recalculated every solve, converting it to a survey point transfers all its coordinates to the point's properties, so they are no longer recalculated. A message will appear indicating that one point without survey data was converted, and its coordinates can now be seen in the properties. The point's status changes to survey. You can immediately bake the entire scene via Edit, Bake Scene. The coordinates of all points will be stored in their properties. If any point was solved incorrectly, you can select it, change its status to survey-free, and resolve the camera. After that, you can bake this point again or leave it unbaked.